Great. Thanks a lot for the invitation and the introduction. It's great to be back at Maryland virtually. It's a little bit of a mixture of two topics. So there are two distinct topics, but I saw that there was a lot of previous talk about NTK. So I thought, maybe it's good to give an update beyond NTK, right? So that's why like the first part is focused on feature learning via gradient descent. So somehow it's not, okay, here we go. So it's really kind of an early attempt at understanding feature learning. So, of course, talking about foundations is a very contemporary thing to do these days, right? Like, there's a lot of talk and papers about like foundations, the theoretical foundations for X, right? X is deep learning, reinforcement learning, AI, and so on. And, I've done a lot of these myself, right? But, over the past year or so, I keep thinking like maybe our foundation is a little bit shaky, right? So this kind of is an attempt to overcome this. So let me kind of argue very briefly, why is it that I think we need a little bit stronger foundations, right? Like there's kind of two aspects to it in the context of deep learning, at least, is that even though we have a lot of nice theorems, they're so far unable to explain a lot of contemporary practices. But let me mention some of them. So one example is like choice of architecture, right? Like whether you use a fully connected network, a convolutional one, a transformer network, right? We don't have a lot of insight why that happens, why any of those are good. Another example is normalization. There's all sorts of normalization, batch norm, layer norm, instant norm, many others. We also don't have a good insight about that. And furthermore, we don't have a lot of good insight in some of the more contemporary practices over the past few years, especially for neural networks. This often have to do with the ideas of representation learning, ideas like pre-training and fine-tuning, even knowledge distillation and so on, right? So that's kind of the more, the more high-level viewpoint of why I think we need a little bit better understanding in terms of theory. But, there's even a simpler answer, which is our existing theory even fails us in toy settings, right? Forget about those contemporary state-of-the-art problems. Even in toy settings, we're in trouble. So, and often the reason for that is that the existing theory often operates with unrealistic hyperparameter choices, right? It could be very small step sizes, very wide networks, very large initialization scales, and so on. Just to drive this idea home, just to make it clear what I mean by this, consider just fitting one hidden layer neural network to a bunch of data points in 3D. So nothing too complicated. So if you use the theory-oriented hyperparameters, this is the kind of surface that you get. Whereas if you use the parameters that's often done in practice, you get much smoother and nicer surfaces, right? So the short story is that in some sense, the existing theory does not apply in practical regimes. And, you might think like choice of hyperparameters doesn't seem that important, right? But actually it is, because neural networks is a very rich function class. How you train them, what hyperparameters use, it actually is very important in terms of behavior, right? And so that's what this first part of the talk is roughly going to be about, is trying to get a theory that is a little bit stronger in that sense. So, and the focus is going to be the focus similar to a lot of, previous talks early on in the class, which was about overparameterization without overfitting. So here, of course, the mystery is that in modern neural networks, often you have way more parameters than training data, right? And you expect overfitting to happen. What happens in practice is that you get a very good fit, right? So there's kind of two mysteries associated with this. One is, optimization, just to also help, make sure we're on the same page on what overparameterization means. Let's look at this very simple example. Imagine you have a planted model in the sense that your data set is generated according to a free hidden layer, a one hidden layer neural network with 3 hidden nodes, right? And then you also train a model of the same size. If you do this and then you run gradient descent, you'll see that you hit a local optimum, right? Now, if you repeat the same experiment, but you pick a larger model, you overparameterize, you add more hidden nodes, all of a sudden you get to global optimality, right? So you don't hit local optima. So that's kind of like the first mystery, which is like, why is it that gradient descent in this context converges to global optima? In particular, if you use small random initialization as is done in practice. So that's kind of mystery one. The more interesting mystery by far, though, has to do with generalization, which is especially because we're overparameterizing, right? There are many global optimum in the training loss. So the training loss, this is a cartoon picture. It looks maybe something like this. There's a lot of global optimum, and you converge to different global optimum depending on where you initialize, right? So if you use this as the initialization, maybe you get to a global optimum with a certain test loss. If you initialize somewhere else, you get a different global optimum which has a different test loss, right? And although this is a cartoon picture, this actually holds in practice, which is that you can in fact reach different global optimum by just playing with the size of your initialization, right? And so in our previous example where the model was planted, in fact, we can repeat that experiment. Again, the data is according to a one hidden layer ReLU network with 3 hidden nodes, and we're just fitting a model of larger size to it. And here, what I'm doing is just changing the scale of initialization in the sense that initialization is always random, but I'm playing with the standard deviation of the initialization. That's your x-axis, right? So what you can see is that I always get a global optimum. So if I draw the training error, right, I always achieve global optimality. But if I look at the test error, I see radically different behavior, right? If I use a small scale of initialization, I get very low test error on the left, but on the right, I get very large test error, right, which is large scale of initialization. And so the problem with existing theory, even in this toy setting, is that it operates on the right-hand side, right? This is the regime that you've heard about before. This is the so-called neural tangent kernel regime, lazy regime, linear regime, where essentially neural networks behave like linear on top of certain features or kernels, right? So essentially what it means, neural networks behave like kernels. So you get some generalization performance out of this, but it's a crude upper bound at best, right? But what the interesting part is like here, right, where you use small initialization and you get good generalization. And so here, really, the question we're trying to answer is like, how do you get, how do you establish generalization of gradient descent from small random initialization, right? So that's the critical question. So just a quick reminder of what this NTK or lazy regime is in this context. So if you're fitting a nonlinear model to your data, right? So here xi's, this is a regression model. So xi's are your input, yi's are your labels, and doesn't even have to be neural networks. You have a general nonlinear function that you're trying to fit data with. So you can model it like, this nonlinear equation. If you look at the gradient update, it looks something like this. So the gradient is like kind of Jacobian transpose times residual. This Jacobian is the Jacobian of the output of the model with respect to the parameters. So that's what it is. And so basically this kind of NTK or linear theory, again, you've seen this before, so I'll be very brief about this. Basically says that if you have the right assumptions on the Jacobian matrix, right, then basically along the trajectory of gradient descent, the network behaves linearly in the sense that you can basically model the performance of the network as as its linear approximation at initialization, right? This is the formula you see at the bottom. So the conditions, the technical assumptions under which this happens is not important. All you kind of need to know is that, at least in the context of neural network, if the network is sufficiently wide and if the initialization is sufficiently large, you basically get this behavior. So, even though the network is actually nonlinear, the dynamics of training essentially, in this regime behaves as if it's linear with some nonlinear features, right? So that's the NTK regime. And, this is a brief history. Like we worked on this kind of linearization principles a few years ago. Later on, it was kind of popularized under like the acronym of NTK. And a lot of us, including myself, worked on it. And there's a lot of cool results in the space, which you've also heard about many of them in this work. So, but what is the problem with this NTK regime, right? I already talked about it in the context of, you don't get actually the right generalization error, but let me give you a slightly different perspective, just a visual perspective of why it doesn't learn the right features in some sense. So again, we're using our running example, but let's just have a visualization of our running example. So I have a one hidden layer ReLU network as my training model. What I'm going to do is for visualization, I'm going to embed each of these nodes as points in higher dimension, each of the hidden nodes, right? So, but the way I'm doing that is like I'm assigning the input base times the corresponding output as like basically the geometric depiction of that node, okay? So that's how I kind of keep track of the nodes. So if I do this for all the nodes, I get like basically a bunch of points, right? In the width dimension, the same as the input dimension, essentially. And then you see that I have 3 black lines there. Those black lines are basically the directions of my planted model. Remember, I had like one hidden layer that generates my data, and that had exactly kind of 3 hidden nodes. So those black lines are the directions of those lines, right? In my planted model of basically the first layer, right? So that's what those black lines are. So in this kind of non-lazy regime where you actually start from small initialization, right? This is how gradient descent works, right? You see the nodes, all of them start small, but eventually all of them align themselves with one of the 3 planted directions, right? So if you run gradient descent long enough, this is what will happen. Now in the lazy regime or the NTK regime, what happens is, that it's the picture on the right. Basically, you can see the nodes move around a little bit to make the training error 0, but they do not find any notion of simple model or learn any good features, right? So in no way have they actually learned, the planted model, right? And in fact, you can see it's like a chaotic a little bit, like there's no notion of simplicity to which they converge to. And so this is a high level. This is why, this lazy regime or the NTK regime is not working so well.
Mahdi, interrupt you for some questions?
Yeah, of course. Yeah, of course.
So in the lazy regime, this is very interesting. So what happens, is it possible that your model may converge to like some permuted version of these vectors because your solution is not unique, right? Because you can have potentially other models that can represent your planted model. So is it possible that it may look like that you are not converging to the solution of your planted model, but you may converge to like some equivalence class of it?
Yeah, it could be. I don't think this is the case here, but yeah, that's a good point of view. I think, some of the equivalence classes is kind of covered by this picture, right? Because, obviously we're not asking you to asking the model to converge to exactly the same bits, right? You see, like it's only different ratios of the same bits. But yeah, you are right that maybe, maybe some of them could be a linear combination of those bits, right? But at least I think for one hidden layer, it is capturing, especially for ReLU, it is capturing all the permutations that I know, which is just like scaling, right, between the input vector and the output vector. Potentially there could be other ones, but I feel like because you have a ReLU nonlinearity, that stops that from happening. But that's a good question. It could be that maybe, there's other equivalent classes that maybe it's not obvious from this picture.
There are some questions in the class, so I'll take them. Yeah. Yes.
So my question is regarding the non-lazy. What do you mean by non-lazy initialization? I mean, NTK initialization. Do you mean that? So NTK initialization sort of has a criticality, right? Where you initialize it there, then you have a theoretic initialization.
Yeah.
Do you mean by that, or do you just mean the scaling?
Yeah, this is the scaling. Actually, I should have mentioned this earlier, right? There's actually 3 hyperparameters that govern the NTK regime. One is scale of initialization. The other one is the width of the network. And the other one is also the step size. So there's 3, and they're all interrelated in some ways, right? So here, throughout this talk, I'm focusing on one, but you could redo everything by focusing on the other 2, right? here I'm fixing the width of the network and the step size, and I'm just looking at the scale of initialization as the variation. So if you fix the other two, the way NTK, non-NTK kind of like manifests itself is basically by just scale of initialization. So this is how you get into these two regimes if you fix the other two. In reality, all three are connected, and when you enter NTK versus non-NTK regime, it's a combined function of all three things. But I'm just fixing two of them, focusing on one for simplicity. And I think there's a question in chat. I don't know, but I don't think I can read that because if I click, so.
It says, is that related to weight decay? It's from the chat.
So in this experiment, I'm not doing weight decay. So I don't think so, right? Weight decay can help, but in this experiment, I'm not even doing weight decay. Again, here is a regression context, a little bit different from classification. So weight decay is not necessary.
It sounds good. No more questions.
Okay, cool, great. Yeah, but keep the questions coming. You know, this is much nicer if it's interactive. And I should say that this phrase of lazy was, and you know, a similar experiment was coined by Chizo and Bach. So, but I do like this lazy acronym pretty much a lot. So I'm using it. So yeah, but the short story is that existing theory does not apply in practical regimes, and it's very much because you're kind of not learning the right features in some sense, at least in my view. So yeah, like what I'm going to try to do is like, you know, go beyond this lazy regime. And we've been able to do this in a variety of different contexts, but I'll tell you only about one story, right? We've been able to do this for low-rank reconstruction, deep linear network, one hidden layer networks. So I have references to the first one, right, in like the references that you saw. But, you know, because I want to go to the second part, I'll just focus on one hidden layer neural networks. This is probably a place where you can see this more easily. So here, just focusing on one hidden layer networks, in particular, learning polynomials with one hidden layer network. This part is basically joint work with Alex Damian and Jason Lee at Princeton. So what we are interested in here is actually trying to learn polynomials with neural networks, right? And, you know, for this, you know, the toy model that we study is that we assume that the input data is Gaussian, right? The output model is like a polynomial on top of a linear representation. So this U is kind of your features. G is the polynomial head, right? It's a multivariate polynomial, but with scalar output. And let's say it has degree P. U is kind of the representation, right? Or features. Well, U is kind of a fat matrix in this work, right? So the output dimension is, let's say, significantly less than the input dimension. So that's the setting. And you know, even though these are how the labels are generated, right? So that's just the labels. We still learn just a one, you know, to fit to these labels, we just still fit a one hidden layer neural network model, right? With a ReLU, right? So the activation is not polynomial, just the labels are polynomial, right? And we're working on a regression context, so we just minimize the least square loss. And the algorithm is simple, just run gradient descent from small initialization, essentially. It's a little bit more complicated than that, but you know, I won't talk about that here. So with this model, right, this is interesting for study of NTK because actually there's a very good understanding of what NTK can accomplish in terms of generalization error here. So this is a result by a bunch of Stanford people, you know, Andrea Montanari and his co-authors, basically, which says that in the lazy or NTK regime, even if you have an infinitely wide neural network, right? So as rich as you want, you would need at least d to the p many samples, d being the input dimension, p being the degree of the polynomial for you to generalize well, okay? So that's kind of the result. So this is why we thought, okay, this is a perfect setting to actually study the feature learning property because we have a lower bound on basically the NTK regime. What we show actually is that, you know, if you have sufficient number of hidden units, so it doesn't even have to be infinity, right? This, in some sense, is minimal if you think about it. It's r to the p. If you run gradient descent from small initialization, you actually get very nice generalization error. Let me translate this a little bit, which is like, essentially, you need d squared plus r to the p many samples for you to generalize well. If you think about it, the right answer should be d times r plus r to the p, because d times r is the complexity of learning a representation. R to the p is the complexity of learning a polynomial, right? We're a little bit suboptimal, but compared to the NTK regime, we're doing pretty well, right? Because as we just saw, the NTK result is d to the p, the larger dimension. So we actually are getting an exponential improvement, right? Especially if you think of r being as order constant, that then it's really significant, right? So yeah, the point is that you can actually, if you go beyond the NTK regime, you can learn much better in some sense. So this is the result. Now,
let me pause. This is very interesting because you know, definitely you reduce d to r, and r can be much smaller than d. What would happen if your p is 1? Right, so
yes, that's a very good question. You should not think of p as 1, because these numbers are made to more for p constant. These are not the right order for p equals 1. Yeah, but here we're thinking of p as a constant, but not equal to 1. So if you think about it, like even r to the p, well, some of the stuff are not sensible for p equals 1, right? But did you have a particular complaint about p equals 1?
No, I was basically thinking, because in that case, your target is a linear function of your input.
Yeah.
It would be interesting to see which of the lazy versus non-lazy training would basically recover a linear function.
Yeah, actually, p equals 1. I mean, just p equals 1. Okay. I think that has been looked at actually. So I don't know if the sample complexity would be different in this case, right? Well, yeah, even then it would be different. That's a good question. So sorry, I thought you were asking r equals 1 at the beginning, so I got a little bit confused. So yeah, p equals 1 is interesting. I think you still beat the NTK regime, because essentially you get a minimum eigenvalue, whereas you shouldn't really hit minimum eigenvalue of the NTK kernel. That's the reason.
Sounds good. Thank you. I don't see other questions. Are there any questions from the class? I don't see any more.
Okay, so I'll move forward. So let me briefly tell you, like, because I kept saying, like, you know, there's even feature learning in the title, right? So let me, and also I talked about contemporary practices. Let me tell you that, in fact, this has some consequences for that. At least if you consider very toy transfer learning setup, right? Which is, you know, imagine you have little n source data, right? Capital N target data, right? And then, you know, they're still kind of using the same planted model, except that we're now using 2 different polynomial heads, right? Let's say the source data is generated according to the same model, also the target data, but they share the representation, right? So U is shared between them. The polynomial heads are different, right? So it's like if you want to look at this model, it's like a very simple transfer learning set, right? Now, the question is, like, what happens if you actually do what is done in practice in a transfer learning context, which is you train both layers on the source data, right? This is what typically people do. And then you kind of fine tune or retrain the last layer on the target data, right? That's what, again, people typically do. So you freeze the first layer, you retrain the last layer. So this really kind of speaks to feature learning, right? So then in this context, using this model, this is what we can prove again. If you have r to the p many samples, again, if you run gradient descent with after a proper number of iterations, now your generalization error consists of 2 terms. The first term is kind of like for learning the features, in this case, U, right? This is the same kind of sample complexity we had before. So you still need a lot of source data. But if you look at the target data you need, which is the second term, interestingly, it does not depend on the input D, right? Which is consistent with the fact that if you had already learned the representations and you're just trying to learn the polynomial head, the new polynomial head, right? So actually you basically need r to the p target data to just learn the new polynomial head, as if you've already learned the hidden representation, right? So kind of speaks again to feature learning, because it says that, you know, you need very little target data to fine tune, right? That's kind of a picture. Okay, so let me very briefly, I don't want to belabor this point, but demystify why this happens, right? This is very brief. So kind of high level, the key idea here is that there is implicit spectral bias happening for gradient descent. In some sense, gradient descent plus overparameterization plus small initialization behaves kind of some sort of spectral initialization. And by that, I mean, you know, somehow you can understand the trajectory of gradient descent from small random initialization by kind of running power method on certain matrices and tensors, right? And you can see the initial trajectories are basically the same. After you kind of get close to to this global optimum, then they diverge. But essentially, the idea is that I can analyze gradient descent by keeping track of the trajectory of some fixed matrix and so on, right? This is the reason this happens. It's based on a very interesting spiking phenomena. I mean, I have one slide on that, but I can also skip. I don't know. So do you want to see that or not? Let me maybe show it to you on just a simple model. So I won't do it on a more complicated model. So imagine you're trying to learn a nonlinear model, right? So if you write the gradient update, it will look something like this. Now, if you use small random initialization, right, you can basically pretend theta 0 is 0. So most of the terms go away. So you end up with a model like this. Now, let's look at a very simple model, which is just linear model with a nonlinearity on top. So if you write it in this case, this is what it will look like. So, so here you have an empirical average. You can replace it with an expectation, assuming things concentrate. So you get something like this. Now, there's something known as Stein's lemma, which basically tells you that this expectation actually is equal to if you take the expected value with respect to the input x, right? And if you do that, basically theta star pops up, right? So this is what I mean by spiking phenomena, right? Basically, the first iteration of gradient descent kind of almost spits out the right answer, right? Which is the planted model here. So for a one hidden layer model, things are more complicated. In particular, the gradient happens to be 0 because you have a one hidden layer model. There's a more complicated picture. Basically, the Hessian gets involved, and a lot of other things happen. So it's not that simple, but you have this spiking phenomena showing up not in the gradient of your model, but the Hessian of your model, right? But yeah, this is a little bit more technical, so I'll skip this description. But that's essentially what happens. Okay, so let me skip this and let me just try to wrap this first part up. So the idea in this first part was we're going to try to go beyond the lazy regime, and it applies to many settings already: low rank reconstruction, linear networks, one hidden layer networks, and so on. And again, the key idea I want to leave you with is that this is based on a sort of a spectral bias phenomena where at least you can analyze the initial trajectory of gradient descent very well by analyzing some, essentially power method type of techniques on simpler matrices or fixed matrices or tensors and stuff like that, right? So that's kind of the idea. Okay, so this kind of concludes the first part, and then I can go more to the applied stuff, which has to do with deep inverse. So if there are any questions about the first part, this would be a good time to ask.
Thanks. There is a question. Just go ahead.
So the NTK regime assumes that the width is going to infinity and all other scales are almost 0 as compared to that. So I'm wondering if there is feature learning when time is taken to infinity with width. If you take width and so I'm saying if you take width and time simultaneously to infinity, do you get feature learning?
So sorry, I missed the last part.
So I'm asking you, if you take width and time both to infinity simultaneously, do you get?
Yeah, I think there is some work on that, right? Like when you take both of them to infinity. I think people have shown that you exit the NTK a little bit, but I'm not sure if there are results that actually tell you that you actually still learn the right features. You would achieve the better sample complexity we're talking about here. But yeah, so that's like if you want to push the NTK a little bit, you know, you could proportionally make like this time scale and width go to infinity together, right? You get slightly different features than the normal NTK kernel. Good question.
Yes, go ahead.
Yeah. How did you keep track of the gradient descent and the spectral bias curve?
Sorry, can you repeat louder your question?
I mean, the diagram he showed that professor showed that it diverges after the initial. Like, how did you track on the surface of the gradient?
Yeah. So here the idea is that you know, so for example, in this problem that we looked at, essentially in this first phase of training, you get a very good approximation about you, right? After you've learned you, then you can kind of like maybe even switch back to an NTK analysis. But basically, after that, it's kind of a local convergence analysis, right? Like the problem is somehow locally convex or a property similar to that facilitates linear convergence. So that's the idea. If you kind of learn the right features, then you're kind of good, right? Then you can do some local updates to learn the head, for example, in this case. But in general, it means that, you know, you kind of are getting close, at least in some sense, to the global optimum, after which a more traditional local convergence analysis based on strong convexity or, you know, the LP condition, right? The gradient dominance kind of condition would kick in. That's typically what happens.
Right, sounds good. You don't see any more questions?
Okay, great. So let me actually go to the second part, which is a little bit more applied focus. So this is kind of like, you know, I thought I should talk about this because, you know, deep learning, we all most of the time see it in the context of classification. So this is an exciting area where it's more about regression. And it has to do with solving inverse problems using deep learning. And, you know, this area has a very broad motivation by itself because, you know, it's just as a simple example of the use of kind of modern AI in the context of computational imaging or even sciences more broadly, right? So the high level motivation for this area is like, look, you know, maybe you have like if you look at the scientific applications, there's some sort of measurement apparatus, right? You take some sort of measurements, right? If you're not happy with the quality of your measurements, right? Maybe you go buy a fancier equipment, right? You go buy a bigger telescope, you know, like, you know, build a bigger telescope, buy a fancier microscope and so on. And then you get the quality image that you're after, right? But there's kind of a really exciting area with this computational imaging, right, that is coming about, which is like, what if you keep your kind of bad, simple, cheap device, right? Maybe make very small changes in the hardware, but augmented with powerful computational algorithms, in this case, you know, modern neural networks, to actually get the high quality reconstruction or you know, measurements that you want out of the low quality measurements, right? So there's a lot of promise for that. And, you know, I'll focus on a very, you know, narrow area, but, you know, there is a very broad interest in this, in the scientific domain. So, you know, let me be upfront about this. Like using neural networks in this context has a lot of challenges, right? And so this is common also to normal use of neural networks, but I would say here it's even, you know, exacerbated, right? Like it's even more prominent, right? One is the reliability challenge, right? So here's like, you know, in the context of medical or image reconstruction, you could have hallucinations, right? This happens all the time. So especially if you have little training data, right? So you can see if you use 10% of the training data or 1%, actually the algorithms start hallucinating things that shouldn't be there. And in this case, it's some tears, right? And they are diagnostically significant, right? So basically, you know, so the reliability challenge is even more dire here, right? So that's one. And then, you know, of course, if you start using neural networks in this context, you could get misdiagnostics using this, right? Here's another example. This is like in the context of imaging like nanostructures, you can see like the DL reconstruction kind of hallucinates weird stuff, right? Like, you know, it's basically hallucinating a part of the chip that isn't there. And again, this could be significant. There is bias. This is the famous example that became really famous on the internet, right? This is in the context of super resolution, right? So basically, this is a picture of Obama, right, which is like pixelated, right? And if you super resolve it, and you super resolve it in a consistent manner, and this is like what some of the algorithms produced. This is like known as the white Obama controversy, right? So again, these are reconstruction tasks, but you see all of the issues with neural networks even more exacerbated. A more fundamental challenge, if you're talking about scientific applications, is like data scarcity, right? So deep learning, we all know, is data hungry, right? And more often than not, the reason it works well is because you have internet scale data, right? If you look at vision NLP, you can scrape off the internet, and there's so much data available there, right? So data acquisition is easy in some sense. The cost is very low, right, of gathering data typically in these domains, and you have large amounts of data. In the context of scientific data, however, you have data scarcity in the entire pipeline, right? Like, so because, often what you're trying to do is take some sort of measurements from a real phenomena. That gives you one data point. You take more measurements, more data points. This is how you get a data set, and then maybe you feed it into your algorithm. So the data acquisition part is costly because, it could be a very extremely slow experiment, often very expensive to calibrate, right? The data collection is also costly because, a lot of times the measurements, especially if it's a human subject involved, it could be harmful. The acquisition could be harmful. Occurrence of events could be harmful. Recruiting patients, for example, could be harmful, stuff like that, right? Or expensive at least. And then, even often the tasks here are more complicated, so you need more data, right, to do it. So all three parts of the pipeline can get complicated. It's just an example. If you're working in medical imaging, which is mostly going to be the focus of this talk, the data acquisition part often is slow, and also it's harmful because of the radiation. The cost is high because you need to recruit actual physical humans to do these experiments. And as a result, the amount of the amount of public data on this is very small because there's also all sorts of privacy issues, all sorts of other things involved too. So that's kind of like the challenges we face in this area. And then finally, there's also a computational challenge, which is like, even though you have very little training data, the data that you have are much larger and richer and more complicated, right? Like they have high spatial resolution. Typically, there's multiple volumes, right? Maybe there's additional layers of complexity because there's complex stuff happening, right? So that's yet another challenge. And as I mentioned, like there's all sorts of these cool problems and challenges I'm focusing, and it has very broad applications in scientific domains, right? Really a lot of cool stuff happening, right, in the sciences. The focus of this talk is much more narrow, which is on the focus is deep learning for inverse problems. So what are these inverse problems, right? So the basic formulation is like you have some sort of potentially nonlinear measurements from some signal X or thing like that, and then there's noise. So you have measurements, there's a forward operator, possibly nonlinear, and then there's a ground truth signal that you're trying to reconstruct in the middle of noise, right? So if the model is linear, it would be linear inverse problems, right? In this context, usually you have fewer measurements than the ground truth. So that's one issue. And this also means that there's often infinitely many solutions to this. That are consistent with the observations. There's a lot of common inverse problems. The one that you probably heard most of is just denoising, right? If I have a noisy image, can I get the denoised image back, right? That's simple. Another kind of famous example is deconvolution. If you get a convolution of two signals, right? If I know one of the convolving factors, can I get it? And if I don't know both of them, I don't even know the Blair kernel, can I get it? Which would be blind deconvolution. So can I go from the blurry image to the actual image, even if I don't know the Blair kernel? So this is a more nonlinear one. Another example is just image implanting, right? Like if part of the image is damaged, how do I reconstruct that part? Super resolution, this is like the Obama example, right? If the image is blurry or I've subsampled in pixel space, how do I reconstruct? There's nonlinear versions of this. This is like in nanoscale applications. It's called in the phase retrieval. I won't talk about this too much. And then, the one that we're focused on today is basically, for example, MR image reconstruction, right? So here, the problem is like, essentially you get, if you're trying to measure the part of a human anatomy using a MR machine, right? You get basically what you see is like signals in the Fourier transform, right? Like that's what you do. And typically you get a subsampled version of this because again, you do not want to keep the person in the MR scanner too much. Now, the question is like, given these measurements, so you're measuring a part of the anatomy. What you see is like kind of some sort of, let's say, for instance, here, Fourier transform plus undersampling plus noise. And the question is, how do you go back, right? Given the measurements, how do you reconstruct the signal? Of course, the forward model in MRI is actually more complicated. What happens here is like, there's a ground truth signal. There are some coil sensitivity maps that gets convolved with these. Then you do like this linear operation, the Fourier transform. Then you add noise. Then you undersample. This is how you get measurements for different coil sensitivity maps. And then you get using the combination of all of them, you want to reconstruct your ground truth, right? So this is like one popular, linear inverse problem that appears in MR. So these are the formulas, but it's not too important for us. So historically, to tackle these inverse problems, there's a bunch of things people would do, like at least a linear kind, right? So because you typically have more parameters than measurements, right? Or you have more unknowns than measurements, there's no unique solution. So people find kind of a best surrogate solution, which is consistent with your measurements. Early on, people would just use the least norm, right? So that's what people typically did. And so then there was a literature which said, okay, what if you use more side information to do better than least norm? So basically this led to these ideas of compressed sensing, which was, well, I'll try to find signals that are consistent with my measurements, but at the same time, maybe if I have some prior knowledge about the signal, maybe I'll enforce that using a regularize, right? Oftentimes in this domain, it was like the regularizer is like some notion of sparsity in a Fourier domain, in a wavelet basis, some sort of basis. So that was the idea. And the way you would solve these is by basically an iterative technique to solve this kind of optimization problem, right? But more recently, maybe I would say the past 5 years, there's kind of more data-driven methods that leverage training data directly for this inversion, which is essentially, I'll only talk about the supervised kind. You just gather a bunch of training data, which is like input measurements, right? The corresponding output, right? Output measurements. Can I directly from those learn the mapping directly, right? That maps the two, right? So that's kind of the more modern perspective on this. So there are two approaches to doing this in this data-driven world. Both are neural network based. One is based on generative priors, which again, I saw that there was a wonderful class already on the generative modeling. So I'll just talk about how you would use it in this context. So here the idea is that roughly you learn the distribution, the input distribution of the input or the ground truth, and then you try to implicitly enforce it in your reconstruction. And yeah, there's a generative network that uses that. I'll explain this more in detail. And then there's also like kind of end-to-end methods, which I found bizarre at the beginning, but now I'm getting used to them, which essentially says, I'll just gather a bunch of training data of input ground truth, the corresponding measurement. Then I'll try to find a mapping that directly goes from the measurements to the ground truth, right? Which is kind of crazy if you think about it, but it works very well. So I'll talk about both a little bit and then tell you what's new. So let's see how these deep generative model works in the context of inverse problems, right? So again, there was already a class on this. You know how deep generative models work. So essentially the goal here is to efficiently model high dimensional data, right? And the idea is you learn mappings that go from simple seed distributions, for example, Gaussian noise, to complex distributions, right? And often the way you parameterize this is using a deep neural network. So you're kind of like trying to estimate the distribution of your data as well as you can. And to do this, you also minimize some sort of loss between the generated distribution and the true distribution. And this is how you get stuff like this, right? You go from random noise to realistically looking images. But how would you actually, this is like, as generative models have evolved, similarly, their use in this context of deep inverse have also evolved. So, first people started using variational autoencoders, then GANs, and normalized flows, and of course, these days, diffusion models, right? But let me tell you how you would actually use generative models in this context, right? Basically, in this context, what you would do is you would actually, given the input training data, right, you would try to kind of learn a GAN model that basically learns the distribution of your input data variable, right? So that's the first step. This is very similar to how you would train GANs anyways, right? So same thing. So you kind of train a GAN to learn the input model, and then you leverage the kind of the generative prior that you learned from the input data for reconstruction, in the sense that now if I have a new measurement, now I've trained the parameters of the GAN, I'll just try to fine tune the input of the GAN now, right? To match my measurements when I pass it through the forward model, right? So you minimize this, right? So if I have a new measurement, I'm basically using GAN as kind of an implicit regularizer, right? Like the output, right? So essentially you're trying to find a vector in the latent space of the generator, right? That corresponds to the right measurements in your output, right? It's consistent with your measurement of observations. So, and there's a very interesting paper by Alex Demarcus's group and Eric Price on this, right? For the use of this.
So Mahdi, can I pause you here?
Yeah, of course.
So in this optimization, basically we find a latent variable Z in a way that is on the manifold. Basically, the G of Z, transformed by A, matches the measurements that we have. Right?
Yeah, exactly.
We don't take into account any posterior distribution on Z. Like the Z that we find may be far from, let's say, a normal seed distribution that you have, or if you like a VAE, if you look at the distribution Q, Z given X, which is basically Y here, then that Z may have a very low probability. So how do you think that would affect the performance?
Yeah. I mean, that's a good question. I think the idea here is that so somehow, and I agree with what you're saying, because maybe you're out of distribution, right? But the idea is that somehow using the first step, you kind of learn the manifold of the data, right? Like your parameters of the GAN learn the manifold of the data, and then all you need to do is kind of fine tune the input starting from a random Gaussian seed, right? But again, I agree with you, because potentially you're not actually sampling from the Gaussian distribution anymore, right? So you could go, in some sense, you're not, your input is no longer Gaussian. So it seems a little bit strange, right? But yeah, it's kind of like, maybe you've learned the manifold, you're just fine tuning the parameter a little bit. It's a good question. Yeah, and people did observe that this does improve over classical sparsity-based priors, right? So using GANs in this context, for example, this is what they used back in the day, does improve the reconstruction by a factor 510. In the sense that for a fixed reconstruction, you could get away with using 5 to 10 less measurements, right? So which is nice. And people also use it in all sorts of other contexts. For example, this Pulse paper that caused the controversy, right? With the white Obama, it's using basically a kind of fashion, like a more, more contemporary GANs to do the super resolution, right? The idea is coming from kind of the more advanced GAN literature. Which is very nice. You can see the reconstructions are really very good, right? You can really find very high quality reconstructions that is consistent with your measurements, which is amazing. So these ideas work very well, but there's a kind of a problem with them, which maybe actually goes back to your question too, right? Which is like somehow these GAN based modeling, right? they actually start to fail. They work well when you have very little measurements, but very too little. But in the more practical regimes where you have a moderate size of measurements, they actually sometimes even perform worse than the classical techniques, right? But the fact that they might perform worse is not the issue. Somehow, the issue is that they seem to hit an error floor, right? Like you can see this, right? Like the performance stagnates, right? They don't keep on improving, right? Which is a little bit strange, right? Which may actually go back to the issue you're raising. So if you can fix that. And even the fancier GANs you use seem to make this error flow go a little bit down, right? But the error flow always exists, which is very strange, right? So this is kind of an issue for using GANs in this context, which I think is very interesting to look into how you can fix it, right? And then the other techniques is like end-to-end methods. These are, at least in the context of MR reconstruction, these are the techniques that are kind of like been very successful, which is, again, it seems a little bit strange, right? But you try to directly learn the mapping that goes from measurements to your reconstruction, right? You just try to learn the inverse directly, right? Using a bunch of training data, which again, like first time I saw about it, like, no way, this is very strange, right? So here you want to learn a kind of you want to reconstruct X from A. What you do is just gather a bunch of training data, input X corresponding output measurements, right? And you literally try to learn a network, right? That goes from the measurements to the input. And you do this by minimizing some sort of loss, right? Like as it's done in anywhere in neural network, right? And again, like I was personally very skeptic, but you just look at all of these results, right? On like this fast MRI data set, which is a public reconstruction data set, all of the top performing teams are end-to-end. So these techniques work really well. So let me tell you a little bit about the history of these techniques, and I'll tell you very briefly also about what we did in this space. But this is more just to familiarize you with these kinds of class of problems, right? So the first kind of networks that were used for this context is UNet, right? Their name comes from the shape, right? Essentially, there's a combination of downsampling, right? So you can see the latent spaces become smaller and smaller. And then upsampling again, right? And there's a nonlinearity all everywhere, right? So the first layers are convolutional. So it's a combination of convolution, downsampling, and so on, right? And then you finally get to the low-dimensional latent representation, and then you try to go back, right? So you do now spatial upsampling, another convolution, and then the final innovation is that there's also a direct skip connection, right, to the output. So this is UNet. This actually was the first kind of networks that worked well in this end-to-end fashion. But UNets were not sufficient, so people had to go a little bit further. I have a kind of an intuition for why going further works, but let me skip this intuition and directly tell you how it works. I just had like a toy example to demonstrate how it works, but let me just skip to the chase. What units did not work that well. There was a good baseline, but what made them work really well is the combination with unrolled networks. So what is unrolling? So this unrolling goes back to how we used to solve these kind of inverse problems, which was the idea was like, you have some sort of consistency, kind of data consistency term where you're making sure your measurements are consistent with your the output of the model, and then using some sort of regularizer. So if you were to do this using an iterative reconstruction technique, this is what the gradient update would look like. The first term is like the gradient of the data consistency term. The second term is the gradient of the regularize, right? So the idea behind these unrolled networks is like, what if instead of the gradient of the regularizer, I just put a neural network, because in reality, I don't know what is the best regularizer, right? So why don't I just directly try to learn the gradient of the regularizer? Because after all, I don't know what is the best one to use, right? What is the best regularizer? So I'll just parameterize the regularizer of the gradient of the regularizer as a neural network, right? So this leads to like something like this. So I start from my input or from my first iteration. I have a data consistency term. And then I have a kind of a neural network, which is supposed to model the regularize, right? And then I iterate. So, but as I iterate, I just use a different neural network in every iteration. I cannot iterate to infinity, so I do this only a finite times. So this is called unrolling, right? So I'm somehow unrolling the gradient iterations. Instead of the gradient of the regularizer, I'm just plugging in a neural network, right? And typically the amount of unrolling is somewhere between 4 to 12, so you don't do too many of these, right? And then now you just plug in units, for example, in this case. Then all of a sudden this works much better. And in fact, this is kind of the state of the art, well, at least before the kind of stuff we did, this was the state of the art. Like this is E2E varnet. There's kind of 2 further modifications on top of that. First of all, they realized that it's better to do this unrolling in Fourier space, or what in the MR domain is called K space. So they did this unrolling kind of in the Fourier transform. So that's one thing they did. And then they also decided that, you know, as I mentioned, the MR pipeline was more complicated. There's some coil sensitivity maps, right? So you have a slices, right? Because you have different coils. You do the Fourier inverse, then you kind of somehow merge them together. Then you put the neural network in the middle. So they also decided to learn the coil sensitivity maps directly from the data using a smaller neural network. So that's what they did. And so if you do this, then you know, and the denoiser in this case would be just a unit. This is like kind of the state of the art, right? So if you look at it has been kind of state of the art since 2020. This is the fast MRI public leaderboard. So here the reconstruction is measured in SSIM. It might look like the improvement over the previous one is not significant because it's in the 3rd digit, but this measure, which is SSIM, is very sensitive. So even the 3rd digit improvement is actually visually significant. So this is what people did, right? Like, and this was the state of the art, except for one other team, which you know, is a private company. They've never released their code, so no one knows what's going on, right? So this is has been state of the art since 2020. So we thought, okay, so when we came into the picture, we thought, okay, well, can we do better with more modern architectures, right? In particular, and yeah, this it's now, I guess, almost pushing on 3 years, has been constant. So this is our technique, is what we call the hummusnet. I did not come up with this name, but you know, I can take credit for it. So this is joint work with my student Zalan, and then another student also recently joined the team, which is Bert. So which is like, could we use somehow transformers in this context, right? If you're smart about it. So transformers have a lot of advantages if you think about it in this context, which is like, we know that convolutional kernels are content independent. You use the same kernel regardless of which part of the image you're looking at, right? Whether it's like the bone, like skin, tissue, whatever. And then we also know that that convolutions are not efficient for modeling long-range dependencies. This is, after all, why transformers are used in NLP context. For example, in this case, if you have a piece of bone on one side of the image and then you have the same piece of bone on the other side of the image, convolutions can't capture these dependencies well, right? So it kind of makes sense to do this. And of course, as you all probably know, like the way this is done is through a self-attention mechanism. I will not go into that, right? So this is like a, you know, there's a self-attention mechanism where you pacify the images, you know, and then you create these attention blocks. The one thing I do want to mention is that one issue here is that this self-attention mechanism, the complexity is quadratic in the number of patches, right? So that's something to be aware of. So to deal with this quadratic scaling of the patches, people have actually looked into that because there's like these sort of vision transformers. So what people often do is use a local window attention, right? So here the idea is that so we don't have to deal with this quadratic number of patches. Essentially, you have more, you know, the patches are not equal. So you change the size of the patches. And every so often, you kind of shift these patches, right? So that's roughly how you scale, deal with the scale. People have documented that this kind of gets you more or less to linear scale in the patches. This is called local window attention. And, you know, using this combined with a little bit of convolutional network has been shown to be very effective at denoising, right? This is things known as the Swine transformers. They're documented to be very good at denoising and you know, super resolution. So the reason they seem to be very good is like they're transformer convolutional hybrid essentially. So they have the benefits of long range dependencies via the self-attention mechanism, but also somehow they have the implicit bias of convolutional networks, which is we all know are pretty good for images, right? So we thought, okay, what if you use these Swine transformers in this unrolling schemes, right? And what we did was like, we picked the largest ones that would fit in into our GPU's memory. Like our GPUs are not super fancy, but they still have better memory than most, right? But once we did that, you see like validation SSIM, which is this metric, higher is better here, was not good, right? So just unrolling these Swine transformers, they don't work. So then we thought, okay, maybe it's because we need to make it multi-scale, right? Because in a lot of signal processing applications, it's good to look at the signal from multiple scales, right? So that's what we tried next. You know, we thought, okay, UNet, one of the advantages is exactly because of this multi-scale. What if we try to make these kind of Swine transformers multi-scale in some sense? So we added, you know, again, by doing convolution, a little bit of upsampling, downsampling like UNet, right? We got to this multi-scale hybrid feature extractor. So this is kind of a multi-scale version of Swine transformer. Performance did improve, right? So if you go from unrolled Swine transformer to the multi-scale version, you get a significant improvement. Again, like even per digit improvement is important here. So this is pretty good, but still we're not there, right? Not as good as Barnet. So again, we use the largest one that fit into memory. So what we realized is that the challenge here is that unlike the use of transformers in the classification context, here the inputs are high resolutional and the prediction task is also very dense, right? So if you look at use of transformers in the basically for image classification like VIT, you have a bunch of patches, right? Patches are typically large. And the original images are somewhat small, right? They're low resolution. You create these, you know, using transformers, you kind of create like these token embeddings, right? In this case, it would be 196, right? And then you pass it for a vision transformer block, you get the classification model. If you try to do that here, first of all, because the input has larger dimensions and requires higher spectral resolution, you actually have to do very small patches. So the token embeddings are just gigantic, right? So that's kind of one challenge that makes it difficult. This is why, you know, we hit this, you know, the largest network that we seem to be able to fit into memory is not good enough because just these token embeddings are huge. There's a huge memory drain. So we actually tested this idea of like maybe using larger patches. So just to show you that larger patches don't help, right? If you just double the number of patches, instead of using 1x1 patches, we go 2x2. Again, we see a significant drop in performance. So you cannot actually get away with using larger patches here. So then we thought a little bit, so how do we fix this? So our solution was to basically kind of process the data in two different kind of levels, right? We first extract some high resolution features, from which we extract some low resolution data. We pass this to our kind of like multi-scale hybrid feature extractor. And then we also go directly using a kind of a, you know, again, like almost like a ResNet block. And then we have a high resolution image reconstruction on top of that. So this with the residual part, this is everything combined. This is what we call the HummusNet, right? So this is our feature extractor. And of course, you know, this is the blocks. We also unrolling K-space as the VarNet does. And then one additional thing, which is also very useful here, what we do is we do adjacent slice reconstruction, which is like, even though we're just interested in reconstructing them one slice at a time, what we use as the input is like the concatenation of two nearby slices also. And so that's what we feed in, right? And then we take the average, you know, to get the middle part essentially. So this is like this is a known trick in this context. So this is not really our contribution, but it's known to boost performance of all of these techniques. And so using all of this, if we applied it in like this fast MRI context, we actually finally are able to beat, bottleneck. Again, the improvement is in the third digit, but as I said, this improvement is actually significant, even visually. And just to show you, like this is, if you look at all of the state of the art, the improvement is always in the fourth digit. So we're happy about the third digit improvement. But to be honest, this is not our main goal. So this is also results on a different data set. So just so that you see that it generalizes across data sets. This is on a Stanford 3D multi-coil knee data set. So again, HummusNet improves in the different metrics. And our reconstructions are actually pretty nice. If you compare them with the ground truth, they're very good quality. But I'm getting toward the end of the talk, but let me tell you what excites me most about this, right, is not so much that we get improvement with 100% training data. The dream is actually somewhere else, right? And we've started working on this, right, which is like, can we do this with much less training data? This is why we started looking at transformers, because we believe they're very good at this, which is like, using other techniques, right? Like, for example, data augmentation, contrastive learning, stuff like that. Can we actually get these networks to work with much fewer training data? Here, training data is not the number of measurements, it's actually the input-output measurements that you collect, right? So what I'm plotting on the blue line is that you can see if we use 1% of the training data, the performance of these classical networks degrades significantly. And so we're kind of working on different techniques and architectures to improve this. The red is where we're kind of at right now. We also have some contrastive versions which look like the green. Our dream is more like this, and this is where HummusNet is, which is like, can we at some point get basically very little drop in performance, even though we use like 1% of the training data? And just to say again, like these metrics are very sensitive. So there's actually visually very significant difference between these two endpoints, right? So that's kind of our dream, right? This is why we started looking at it, because we believe that transformer networks are very good. They already work better in 100% training data, but that's really not our target. Is like, can we make them work very well with very little data? So with that, I mean, I think, it's better if I stop and take questions. I have other techniques here, right? I should mention that one reason, maybe this is the last part, one reason we're interested in making these work with less training data, that we've observed that if you make these methods work with less training data, they tend to be, basically you come up with good methods to do this, they tend to be more robust to a variety of things, right? Like if you have distribution shift caused by using different scanners, right? You have one scanner at train, one scanner at test time, it improves, right? If you can manage to make them work with less training data, these metrics also improve. If you use them in unknown anatomies, you go from knee to brain, again, you observe an improvement. If you manage to train networks with less training data, you even manage to remove some of the hallucinations that I talked about earlier. So this is why I'm really excited about being able to train these using less data. So that's kind of like all I want to say. That there's like a whole class of other techniques that it's better if I skip. I'm happy to tell you more about it some other time. So let me just wrap up by saying that, this area of deep inverse is very nice, right? I think it offers a lot of opportunities, a bit different from the normal classification context. But a lot of the challenges that people have looked at, perhaps a little bit better in the context of classification, has not been looked at, right? So I talked about like, and in some sense, they're even more dire and critical here, right? If you have hallucinations, if you have critical reconstruction errors, if you have bias, you can see it much more vividly in this context. This is a question for Sohail, actually. I do not even know what the equivalent, like this slide is empty, because I'm actually very curious, what is the equivalent of spurious correlations here? I'm sure there is one, but it's not even well defined unlike the classification context. So it's a very interesting question, but also very important one to identify like sources of spurious correlations here. And again, like one of the things, as I said, we're working on it, but I think this is super exciting for scientific context, is like, how do you reduce reliance on training data? This, I think, is going to be critical. Yeah, and with that, let me end it here. Just briefly mention, like, there's also a lot of other exciting applications, like once you figure this out, that this is very useful for, but this is more MR specific, so I'll skip this. Yeah, so let me go to the end. Thank you.
Fantastic. Let's thank Mahdi for this meeting. We have time for a couple of questions. I saw one question on Zoom, but like, are there any questions from students in the class? Maybe I'll start. I think, you should talk offline about the spurious correlation one. I don't want to speculate here, but in the previous version of like the vision transformer, when you said like, people are using like 1-by-1 patches, basically it will be individual pixels, right?
Yeah. So for in this context, that's the problem. Like, if we don't use individual pixels, it will not work well, basically. So a lot of our creativity has to do with dealing with that, basically. So yeah, let me find that slide. Yeah, here, right? We use individual pixels just because we had to, because even if we made it 2-by-2, then the performance would drop significantly, right? You see, like, I do not, I think it's because the reconstruction task is very dense, because you're actually reconstructing a signal rather than just a, classification target, which is just classify the object. So it seems like you need to know the fine details somehow, because you're reconstructing the entire image, right? Yeah.
There's a question on Zoom asking, is there a guarantee to avoid hallucination?
So yeah, I mean, what we do is like, of course, our post hoc, which is just we look at the reconstruction images, maybe show it to radiologists, see if there's something that is missing. But yeah, there's no, actually, this is one of the problems, right? Like, with image reconstruction, there's no good actually computational metric to say, did we do better or not, right? Even like the metrics that you see is not that great, right? Because, this is better than classical methods like PSNR or something that measure image reconstruction for medical imaging, this SSIM score. But at the end of the day, in this context, the only valid thing to do is basically assemble a panel of radiologists and see which images are better, right? And we've done a little bit of that. So, but so in that sense, this is also an important question, which is like, do we have any good metrics, right? Or at least, do we have computational metrics specific, for example, to hallucinations, more specific to robustness, stuff like that? So, very good question. Unfortunately, don't have an answer to it.
Very well. So one last question. You go ahead.
Kind of follow up, I guess, on that. So sometimes when generative models are used for upscaling on medical images, there was a tendency of basically losing the disease itself, because it's relatively uncommon. So you mentioned that it was a bit more robust towards hallucinations. So does that correlate with also basically reconstructing, not avoiding disease during reconstruction, or have you noticed anything in that direction?
Yeah. So we've observed improvements, as I mentioned, in that metric, right? I think it's because these networks work better with less training data that we're observing this somehow, because that's at least, I mean, again, I don't know if I'm correct about this, but my feeling is if you are able to reconstruct successfully using less training data, somehow you capture prior knowledge more accurately. And that means that maybe you avoid all of those hallucinations and stuff like that. But, it's not a formal statement, unfortunately. So that's my perspective. But, it is a really important thing, right? In this literature, which is like, how do you know you're not hallucinating, right? And even like when should the algorithm tell you, look, like this is just not enough data for me to make a decision, right? This goes back to the pulse example, right? So, you can clearly see if I have 2 pixels, maybe my GAN can reconstruct something very nice, right? But at some point, like 2 pixels is not enough to get an Obama picture, right? It's just not enough, right? You're hallucinating. So I think what would be nice in this literature if there was some sort of guardrails, like saying like the algorithm gave you something saying like, look, like this number of measurements, I can't do it. Like no one can, right? or yeah, with this data points, I should not be reconstructing to begin with.
It's, you have a follow-up on your follow. Okay, go ahead.
Yeah, just to follow up on that. Use structural similarity. Would you say like that's the best metric for this type of thing, or like what are your thoughts in general?
Well, SSIM is a good one. I don't know if I would say is the best one, right? I think people have documented that SSIM is a relatively good one for MR reconstruction. There are papers that show it somewhat correlates to radiologist preferences, right? But still, like I think the kind of gold standard is really to put a panel of radiologists together, see how they decide, right? So I've actually had a personal experience with this, which is like sometimes radiologists, if you give them clean images, they don't like it. So one thing we've had to do when we give this to panel radiologists is you should add a little bit of noise because they do not like very sharp images for some reason. So you can see like at the end of it, it's correlated, but it still does not capture what radiologists want. So it is a complicated thing.
All right, fantastic. Let's thank Mahdi one more time.
Thank you.